All right, here we go. I am gonna do some more examples of areas in the plane or the areas bounded by curves. If you successfully complete this stuff, you should be able to find the areas between any curves, both in terms of x and y. And whenever we see certain phrases, we're going to be, in this case, not using signed area, meaning sometimes when you integrate, you have positive areas and negative areas. When we're talking about areas bounded by curves, those areas are always positive. Whenever you're doing any of these, find the area of the region bounded by the graphs. First, sketch out those graphs and find intersection points. So let's see, what does x equals y squared look like? That's a parabola opening to the right. And x equals 10. I'll do these in different colors so they're a little easier to see. And we need to identify the region that we're supposed to find the area of. In this case, I think that's pretty easy. That's this region here. If you haven't watched my other video and you need more of an explanation, go ahead and find that. I'm going to assume that you have watched it, so I'm not going to do a ton of explanation. Now, the next thing we want to, like I said, we want to find points of intersection. I didn't do that. Okay. So what's this point? Well, we know it's x equals 10, so that's 10. And what would that be? Well, the square root of 10. This point down here is 10, negative square root of 10. If you don't know how I got those, you just use the pieces you were given. X equals y squared and x equals 10 means 10 equals y squared, and y is the positive or negative square root of 10. Pretty straightforward. Okay, so once we have those intersection points and we've found our region, we need to draw what's called a representative rectangle. When we're integrating, we're adding the area of a bunch of rectangles. Now, this rectangle is not a good representative rectangle. It's definitely a rectangle, and we could draw lots like it. But in terms of finding height and width, the height is pretty difficult to do because that's going to be y squared on top minus y squared on the bottom. And, well, there's an easier way. That easier way is to draw the rectangle horizontally. And so there's my rectangle. Rectangles have an area defined by length times height in this case. The height is pretty easy. The height is this very small change in y. So instead of change in y, we write dy. And what's the length? Well, the length is whatever this value is, and that's 10. Minus whatever this value is, and that's changing. So it's not going to be a number. Turns out it's a y squared. Okay. So that's the area of just this one rectangle. So the total area is going to be an integral of that, a bunch of those rectangles, 10 minus y squared dy. Starting from y equals, what's the lowest place we draw a rectangle? Y equals negative root 10, up to y equals, so rectangle, rectangle, all the way up until we've completely filled things in, up here at positive square root of 10. I'm going to assume you know how to evaluate that, but I'm going to give you another option. If you realize this area below the x-axis is the exact same size as this area above the x-axis, you could have written the definite integral from 0 to the square root of 10 of 10 minus y squared dy with a 2 out front, because then we're doubling the area. And you might think, hey, that's not that much better. You're right, but you do get this 0 as a bound of integration, which is nice because, well, the calculations are easier. You're going to have antiderivative evaluated at root 10, okay, minus antiderivative evaluated at 0. And that antiderivative evaluated at 0, we already know is going to be 0 with numbers like 10 and y squared. I'll let you do the integration. Okay. Find the area of the region bounded by the graphs of y equals square root of x, y equals x minus 2, and y equals 0. So let's sketch those three graphs. Let's see. Always label y equals the square root of x. That doesn't look like y. And then y equals x minus 2. And y equals 0. Okay, let's find the region that we're going to find the area of. That's up here. And so we need some intersection points. Let's see, this is 0, 0. Ooh, up here, can we do that in our heads? I can, 4, 2. But if you can't, what would we say? We would say the square root of x equal to x minus 2. Square both sides. Uh-oh. And 0 equals x squared minus 5x plus 4. Here we go. X minus 4, x minus 1, x equals 4, x equals 1. Well, that seems super weird to get this x equals 1. But if you realize that if we had the other half of this parabola, we would get an intersection point at x equals 1, it's not so crazy. Okay, so now we know for 2, and we're missing one intersection point, but that's pretty easy. We want to know where x minus 2 crosses over the x-axis, or where that thing's equal to 0, and that's, of course, 2, 0. Okay, so should we draw a vertical representative rectangle or a horizontal one? Well, vertical isn't bad, but there is an issue, and that is, well, what's on top? What function is on top of this rectangle or defines its height? Square root of x on top and 0 on the bottom. If I move over to the right a little bit, I need a second representative rectangle, square root of x on top, and x minus 2 on the bottom. Let's go ahead and write that out. Okay. So the first integral with square root of x on top and 0 on the bottom, right, that's a width of dx, starts at x equals 0, finishes at x equals 2. To that, we're going to have to add a second integral from 2 to 4. And then what's on top here? Still square root of x. But now, the bottom of this rectangle is defined by x minus 2. And that's not all that bad, but we can do a lot better if we use a horizontal rectangle. So I'm going to erase, I'll leave those integrals so we can compare. Let's erase and let's draw one horizontal rectangle, and you'll see, hey, this is much easier. So I need a color we didn't use. Let's use this dark green. So now the nice part about this rectangle is it does represent all possible rectangles, no matter where I draw this horizontal rectangle. Its right-hand side is on that yellow line, and its left-hand side is on that green square root of x. Okay, and remember we're trying to find this whole area. Okay, so now we do top minus bottom, or the larger side, which is going to be the line. Minus the square root. But the problem is, or not a problem, there's a hiccup. This height is going to be dy, which means for my line, I don't want to write x minus 2. For my square root, I don't want to write the square root of x because everything should be in terms of y, not x. So I have to go back. Let's see. Pretty easy to rearrange our line. Instead of y equals x minus 2, x is equal to y plus 2. So our line, y plus 2, minus, really it's a parabola, instead of y equals the square root of x, x equals y squared. Okay. And so where are we going to integrate, or where would the lowest rectangle be drawn? The lowest rectangle would be drawn at y equals 0 all the way up to y equals 2. And hopefully you think like I do. This second integral, I'm going to rewrite, pretty ugly. 0 to 2 of, ooh, how'd I do that? Interesting. Oh, bananas. Okay. Y plus 2 minus y squared dy. That's going to be a much easier integral than the top two. So it might make a whole lot of sense for you to slow down and decide, hey, should I draw a rectangle horizontally or should I draw those rectangles vertically? It might save you a ton of work. All right. Find the area of the region bounded by the graph. So we're looking for total area. That area is going to be positive. Let's see. 2 minus x squared. Ooh, 2 minus x squared and 1/2 x. And let's see, what intersection points are these? They may be important, they may not. So this is square root 2, 0, and 0, 2. All right, 1/2 x goes through the origin. Okay, ooh, let's try zooming in again. How'd that work? I don't know how I did that. Oh, well. Okay, so what are we going to do next? We need to identify the region we're trying to find the area of, and that is up here. That's the only place that's completely bounded by these curves. Coloring's fun. Okay, so that means we need these two intersection points. And maybe at the same time, we should be deciding, should we be using vertical or horizontal rectangles? And the answer is vertical rectangles, because with vertical rectangles, the parabola is always on top. The line is always on the bottom. If you draw horizontally, you go parabola to parabola on part and parabola to line on another part. Okay. So let's see, let's go back. We need to find where these two graphs intersect. So they're both equal to y. So let's say 2 minus x squared is equal to 1/2 x. Let's multiply through by 2. 4 minus 2x squared equals x, and 0 equals 2x squared plus x minus 4. Let's see, can we factor that? Are there factors? Did I do that correctly? Well, that doesn't seem to be factorable. There aren't factors of -8 that add up to 1. Okay. Well, I guess we'll do something else. Okay, that might be super ugly. but we can work with it. Okay, I'm going to need that room to work, so I'm going to rewrite my two intersection points, or I guess I'll write them as one, plus or minus the square root of 17 over 4. And that seems at least reasonable. The negative one is farther to the left of the y-axis than the positive one is to the right. We'll just assume those are correct. Now, lucky for me, I'm not going to evaluate all the way to the end. I'm just worried about setting up these integrals. So we're finding the area of that one representative rectangle. Its height is determined by 2 minus x squared on top minus 1/2 x on the bottom. That's the height of each rectangle. And then the width is this super tiny change in x. That's a dx. And we want to integrate. I'm going to write this separately because I'm going to have super large bounds of integration. So can we rewrite that? Maybe we can make this prettier. Negative x squared minus 1/2 x plus 2. I just rearranged dx. And we're going to evaluate negative 1 minus square root of 17 over 4 up to negative 1 plus the square root of 17 over 4. I think you know what to do from there. None of us want to. I mean, the antiderivative of x squared, 1/2 x, and 2 are all pretty easy. Just the substitutions are going to be a little rough. But I'm sure you can handle it. Okay, area of the region bounded by the graphs again. Cube root of x and x cubed. Ooh, inverse functions. How exciting. So cube root of x that's not where the 3 goes. And x cubed. Probably don't need to write that twice. So hopefully you realize this problem could be harder, but we're going to use symmetry to make it easier. What region are we trying to find the area of? Well, this one and this one. But cube root of x and x cubed are both odd functions. So both symmetrical about the origin, and those two areas are identical in size. So we're just going to double an integral. So I'm just going to worry about finding the area in the first quadrant, and I'll double it. Should we use a vertical rectangle or a horizontal rectangle? It doesn't matter. I'm going to choose to use a vertical one because my two equations given are already in terms of x. There's my representative rectangle. And, oh, I'm realizing I didn't find points of intersection. We all know 0 is 0. And then what cube is equal to its cube root? That's also pretty easy. That's x equals 1, which means y equals 1 as well. So if you want to do it the other way, two integrals, this other point of intersection is negative 1, negative 1. Okay, back to our integrals. What's the height of that rectangle? Well, it's cube root of x on top and x cubed on the bottom. The width of that rectangle is dx. We're integrating starting at 0 and going up to 1, and we need to double the total area. Ooh, this seems confusing. Sine and cosine, does that make things harder? Hopefully not. Bounded by the graphs of sine x, cosine x, and on the left by x equals 0. So x equals 0. Let's draw that one first. I have a feeling this is a poorly written question on my part. Okay. Maybe not, though. Okay, let's see. What does sine of x look like? We don't need to draw anything to the left of x equals 0. So here's pi 2 pi. And we need cosine. Well, maybe it's not that bad of a question. We want the area of the region bounded by sine, cosine, and x equals 0. Well, it might be the case, in fact it is the case, that there are multiple regions. This is bounded by sine and cosine, but it's not bounded on the left by x equals 0. So we don't have to worry about that. Let's get rid of all this junk over here. We don't need you guys. We do need a label. Y equals sine of x. But there's only one place that's enclosed by those three equations. All right, should we use vertical or horizontal rectangles? Well, I always like vertical if I can. I'm happy using x's. No matter where I draw these rectangles, cosine is on top, sine is on the bottom, so I'm going to use vertical rectangles. Okay, get rid of these guys. Let's draw one happy representative rectangle. And all we have to do is height times width. What's the height? Cosine on top, sine on the bottom. What's the width? It's a very small change in x. Let's call that dx. And we're going to integrate definitely from x equals 0 up to, oh, you should have memorized this. Where's the y value of sine and cosine the same? Pi-fourths. And if you look at that integral, that's a pretty easy integral for you to evaluate. All right, again, area of the region. Hopefully you're feeling good about this stuff. 6x minus x squared. Let's go ahead and do some factoring. Okay, that's going to help me. Get some axes first. So one opening upwards, one opening downwards. 6, 2, 0. So 6x minus x squared opens downwards. That has zeros at 0 and 6. And x squared minus 2x, that definitely opens upwards, has a 0 at 0, and another one at 2. Okay, so we know one intersection point, that's 0, 0. What's the other intersection point? Up here? Well, let's just set 6x minus x squared equal to x squared minus 2x. So 0 equals 2x squared minus 8x. Factor out 2x and x minus 4. Okay. X equals 0. X equals 4. So this is 4. And then 16 minus 8 is 8. Okay, let's get rid of that stuff. Clean everything up. Realize purple isn't all that great to write with. Did you identify the region we're finding the area of? You go right in here. And have you decided whether we're using vertical or horizontal rectangles? I am using vertical rectangles. Okay, so definite integral. Start with the easy stuff. I already know the bounds are going to go from 0 to 4 because I already know this is going to be a dx. So x equals 0 to x equals 4. And it's going to be, one parabola minus the other. Which one's on top? 6x minus x squared. Which one's on the bottom? X squared minus 2x. Ooh, now we're getting somewhere. X equals 0 and x equals 2. Huh? And put those in the same color. Actually, these look ugly, but this might be the easiest integral to write yet. So, vertical rectangles for sure. Same function on the top throughout the entire region. Same function on the bottom throughout the entire region. Where are we integrating? That's also pretty easy. 0 to 2. What's on top? E to the x. What's on the bottom? Negative e to the x. And the width of each rectangle is dx. So you may have also noticed that we're given two identical pieces. We also could have done the definite integral from 0 to 2 doubled of just e to the x dx. All right. If you've watched this far, I assume you still need a few examples. Or if you're watching this in real time, we are locked up indoors due to the coronavirus. Okay, e to the x, y equals 2. It's got to be above this 0, 1 point. And the y-axis, y-axis. Okay, so what region are we finding the area of? The only thing completely enclosed is right here. And we can do vertical or horizontal. We're all happy with x's. Let's use vertical rectangles. What's the height of, ooh. Don't skip over things, points of intersection. Okay, so we want to know where 2 is equal to e to the x. Okay. So this is natural log of 2. Okay, back to our area. Definite integral from 0 to the natural log of 2 of what's on top. 2 minus what's on the bottom, e to the x, and a width of dx. Let's go ahead and compare, see if anything is easier if we have horizontal rectangles. What color haven't we used? How about orange? If we draw a horizontal rectangle, that might be easier. We don't even have a subtraction. So, on the right, so y equals e to the x, which means x equals the natural log of y. And so we would integrate, let's see, natural log of y minus 0 and a height of dy. Oh, that is easier. From y equals to y equals 1 to 2. I think that is easier. I'd rather do horizontal rectangles. I'm glad I checked.